In this video, we illustrate how to calculate the pH of a salt formed by a conjugate base of a weak acid. Alright, so the problem is calculate the pH of a solution of sodium acetate, which is 0.10 molar concentration. Alright, so sodium acetate is a salt, and when you put it in water, it will fully dissociate into sodium and acetate ions. Right away we recognize that that acetate ion is the conjugate base of a weak acid, which is acetic acid. And what that means is that there will be some acid-base equilibrium the minute that you put these acetate ions in solution. On the flip side, sodium ions are not don't exhibit any acid-base properties, so we don't have to worry about them. Alright, so let's see what the chemistry of sodium acetate looks like, or acetate ions. Alright, so here are the acetate ions, which are again the business end of the salt regarding acid-base properties. And when you put this in water, what you will get is the following. It's the conjugate base of a weak acid, so it will be strong, and what that means is that it can abstract this proton from water to generate acetic acid and hydroxide ions. Okay, this will be the equilibrium, and then what that means is that a solution will likely be basic. Okay, so we are expecting a pH larger than 7 at the end of this problem. Right, so in principle, the strategy for calculating the pH would be very simple. You simply would need to calculate what the concentration of hydroxide ions are at equilibrium, and then that will give you the pOH, and from the pOH you can use the auto-dissociation equilibrium of water to calculate the pH. Okay, a problem that we have right here with that strategy is that we don't really know what the equilibrium constant for this particular reaction is. Okay, so if we start to write it, this will be something like this. That will be acetic acid, H, times the concentration of hydroxide ions over the concentration of acetate ions. Alright, notice that this is a base reaction, so that is truly a K sub B. And notice that we actually don't know this number. Instead, what we know for acetic acid and the acid-base equilibrium of acetic acid is the K sub A of the weak acid, which is as follows. Notice that the K sub A would be the dissociation of acetic acid into protons and acetate. That value is well established, and we've used it before, and is equal to 1.810 to the minus 5. So the question is whether we can use this K sub A value that is well known for the acid, and then somehow be able to calculate that K sub B for the conjugate base. Right? We can recognize here that there are some similarities. We have here acetic acid and acetate, but here we have protons and there we have OHs. A way to reconcile this is to actually multiply in the numerator and denominator by the concentration of protons, and you will see that we will be able to insert K sub A into that expression. Again, multiplying here by protons in the numerator and in the denominator, we can get to the following. Notice that now, right here, we have exactly the inverse of K sub A. Okay, so this is exactly equal to 1 over K sub A. Alright, and then the leftover is just the concentration of hydroxide times the concentration of protons, but that is exactly the auto-dissociation equilibrium of water into protons and hydroxide, which we call Kw. So right away we can then calculate what that K sub B value is, because both Kw and K sub A are known at 25 Celsius, right? So that will be 1.0 10 to the minus 14 for Kw, and then K sub A for acetic acid is 1.8 10 to the minus 5. Okay, so when you carry out this calculation, that K sub B for the acetate ions acting as a base is 5.6 10 to the minus 10. Right, so it will be base, but it looks like it will be a slightly, or a relatively weak base, because that equilibrium constant is quite small. All right, but now we're actually ready to then write the ice diagram and be able to then solve for the concentration of protons from this expression, and then, for concentration of hydroxide, and then be able to calculate the pH. All right, so let's see if we can draw that ice diagram somewhere around here. Okay, so that ice diagram is going to look like this. Initial change and at equilibrium, and here we have our acetate ions, here we have our acetic acid, and here we have our hydroxide ions. And all of these concentrations will be in units of molar, mole per liter. All right, notice that we start with 0.1 molar of the salt, and because the salt is fully soluble, you will get 0.1 molar of acetate ions and sodium ions. Right, so our starting concentration of acetate ions is 0.10 molar. We're going to start with any acetic acid, and we don't have any base to start with in the reaction. Okay, the change then will be the stoichiometry is all ones, so we will have that those will be the changes, and then at equilibrium we'll have 0.1 minus x, x, and x. Okay, so then we're ready to plug this into our K sub B expression and then be able to find what that concentration of hydroxide is. Right, again, K sub B is equal to the concentration of acetic acid times the concentration of hydroxide over the concentration of acetate, and we have all of those values. Notice that in this case that would be equal to the following. K sub B, this is x squared 0.1 minus x, okay, and K sub B is equal to 5.6 10 to the minus 10. Notice that here we can use an approximation that is quite legitimate in this case. Right, we can neglect this x versus 0.1, and we can do that because x is the concentration of hydroxide at equilibrium, but because we know that the equilibrium constant is so little, then we will assume that x is actually quite small as well. All right, so then we can say that this has to be equal to x squared over 0.1, and then your x, when you solve like that, is equal to 7.5 10 to the minus 6. Clearly, with this value of x, the approximation of neglecting x with respect to 0.1 is sensible, it's very legitimate. Okay, great. So then we have calculated the x from the ice diagram, and notice that that x is going to allow us to calculate the concentration, is exactly the same as the concentration of hydroxide. So then we can right away calculate the pH by taking the minus based on logarithm of that number. And when you do this, the pH happens to be equal to 5.12. All right, the problem is asking us to calculate the pH, so we simply now involve the auto-dissociation equilibrium of water, and then this is the concentration of OH. That times the concentration of protons has to be equal to 10 to the minus 14, or the sum of the pH and the pOH has to be equal to 14, and then what that means is that that pH is going to be equal to 8.88. Those two numbers have to add up to 14. All right, so that is a final answer, and to summarize this video, what we've done here is calculate the pH of a salt which contained the conjugate base of a weak acid.